it's going to go. There should not be a shock. If any of you have ever thrown anything, you've noticed that it does tend to hit the ground unless someone catches it. So what I'm going to do is I'm going to take two markers and I'm going to fling them with the ruler. Get that out of the way. We'll do it off that direction. So what I'm going to do is I'm basically going to put the ruler like this. I'm going to flick it like that so that this one, the blue marker here, is not going to be going as fast as the green marker. Because the green marker is going to accelerate farther, the blue marker is just going to accelerate just for a tiny bit, so it won't be going as fast. So green marker going faster off the table than the blue marker. And the question is, which one's going to hit the ground first?
Blue marker.
Blue marker first? Why? This feels right?
Like accelerating less, and it's going to be on the table for less time as well.
Okay, anyone else? All right, form an opinion. I won't ask you why. You have that opinion. So blue, green, tie, and I'm going to leave the neither off. Let's just assume, for the sake of this, that they will not burst into flames all the way down. All right, who says the blue is going to hit the ground first? That's the one that's not going to be traveling as fast. The voice of one, way to be brave. The green. Savannah?
I'm not sure.
Well, just what's your gut tell you?
We'll go with green.
And Ty? 1, 2, 3, and 4. Chigara, did you want to go with Ty? Okay. All right. I also don't want it actually hitting anything on the way down. Let's get that out of the way before I inhale myself. All right, here we go. What was it?
Green.
It was green?
I look like it was. I can't really see.
Anyone else? I guess Emily, you had the best view.
I think it was blue.
Let's do it again.
Sounds like a tie.
It's supposed to be a tie. So congratulations. Hey, democracy in physics works. So, why? The big question is, why do they hit at the same time when green is clearly moving faster than blue is?
Because it's not enough.
This is not what?
It's not like fast enough to really make a difference.
Oh, any of you watch Mythbusters? Sometimes. There's one where they actually test this out with a bullet, and the bullets hit within 1,000th of a second of each other or something like that. How fast it's going is not an issue.
Because they weigh the same?
Because they,
They weigh the same?
no, that I could take. Oh, how about something that's much more clearly different masses? So we got a 200 and a 50 gram mass. Even though those are their masses, their weights would also be, this is roughly 4 times bigger than that. It takes more effort on my part with more mass, but
Are they both like traveling to the ground at the same speed, even though one's going farther distance-wise?
almost there. Chikara?
Is it because the gravitational force is proportional to the acceleration?
Proportional to the mass, and that constant is acceleration. So they both have the same acceleration. Which way? Which way is the gravitational force pulling on them? All of the speed at the beginning was horizontal. That does not affect what's happening to it vertically. So they fall at the same rate. From a different point of view, the green one, or the 200 gram mass, traveled a farther distance, but it was also traveling faster. But they do fall at the same rate. So if I need to figure out the time it takes for an object to sling an object, let's say I want to figure out how fast was this 200 gram mass going, well, I can figure out the time it takes to fall, the time it takes to hit the ground, just by measuring this height and doing a calculation. So that height is 76.4 meters. So 76.4 centimeters, or 0.764 meters. That's the distance it's going to fall. I know that if I just drop an object, it's going to hit the ground at the same time. So I'm just going to use the dropping an object formula, that the distance it falls is equal to 1/2 times the acceleration times time squared. So this is 0.764 is equal to 1/2 times, I'm just going to use 9.8 because these are crude enough measurements as it is, times squared. How do I solve that? Or what would you do first? There's more than one first step.
You multiply both sides by 2 to get rid of the half.
Okay, that's fine. So 1.528 is equal to 9.8 t squared.
And then divide by 9.8.
So t squared is 1 point. Time squared is 0.156.
And then.
Oh, is it 0.156?
Yeah.
Oh, okay. And then. $396? 5. All right, so it takes 0.395 seconds. Units? Seconds. All right, now, I've done things like this before where people are using time. I think we've done it in this class also, where people are using their stopwatches. And I found anything under a half second, reflexes play a major part in it. So calculating it, probably a lot easier. So 0.395 seconds is the amount of time. So all I have to do then is figure out how far it goes out, because as it falls, there's accelerating vertically, but there is no, once it's in the air, there's no acceleration horizontally. So horizontally, I've got a 0, I have a, I guess you could call it horizontal equilibrium. So this is vertical. Horizontal. That's an R. I know that the distance is just equal to speed times time. So let's fling it off. See if I can figure out where it lands. To me, it looks like it landed about there. I'll put the marker there. I'll put the tail of the marker there. And it came off the table about here. And it looks like about 95 centimeters. So horizontally, 0.95 meters is equal to V times 0.395 seconds. So what is the initial speed? Units?
Meters per second. No, meters per second.
So we know how fast the thing would have been going. Now, if I could match the force which I applied to it, or which I can't do, but if I have this, I could be able to predict how far it would shoot up into the air, assuming I could shoot it off at 2.41 meters per second. So if I then slung it up at that initial speed, how far up would it go? Well,
It'd be like, when you do 2.41 divided by 9.8 or something like
okay, something like that. So I know that acceleration is the change in velocity over the change in time. My acceleration, let's assume that up is positive, so acceleration is negative 9.8 meters per second squared. Is equal to 0 minus, because that's my final velocity, at the peak, I'm going 0, minus 2.41 meters per second, divided by time. My math problem is negative 9.8 is equal to negative 2.41 over time. So time is equal to 2.41 over 9.8. Let's do something.
that. 0.245 or 246.
246? Okay. Seconds. So I know how long it is going to be in the air, but I need to figure out how far up it goes. Well, I got a couple different tools to use for that. I could, well, as it rises, as it shoots off at 2.41 meters per second, and then it peaks, what is that final velocity at the peak?
0.
Yeah, so I have right there. So if I start out at 2.41 and end at 0, what's my average velocity?
1.205.
Okay, it's just the average of 0 and 2.41. So for them doing test corrections and miss that, there's a hit there.
Boy, would it be negative?
I said up is positive, so it's still going up. So my average velocity, let's do it the other way. Average velocity is 0 plus 2.41 divided by 2, which is 1.205 meters per second. And it's going up for that long, so I do 1.205 meters per second times 0.246 seconds. So somewhere around 0.3.
.296.
Same thing. Units?
Meters.
All right. So if I could replicate how fast it's going up, it would go up. So, well, just shy of that length. Now, I can't replicate it here, so you'll just have to trust me or trust yourselves when you do the lab. Okay, questions up to here before I make some comments about how to improve this. All right, so let's talk about improving it. If I had some sort of device that could, like a spring device that I could set to the same spring compression every time, that would make it better than just using it with my hand. And so we have these projectile guns, projectile launchers, not guns, projectile launchers, which have springs on them and 3 settings. Whatever setting you end up choosing, you stick with that for the rest of the lab. And I'll show those when we get over there. The other issue is that when it came time to the distance that it went horizontally, I did a crude, I looked at it by eye, and I assume, based upon previous experiences with students, if Emily had pinpointed the spot, she would have picked a different spot than I did. I hope that they would have been close, but did you see where it hit?
Yeah, a little bit, just like where you put the cap on.
Okay, so we're a marker's length off. We can improve that if I have something that it's going to hit. And so a suggestion by a student early on was to use aluminum foil, which works quite nicely. The ball is going to hit the aluminum foil and leave a little indentation right there where the ball hits, so you know exactly the spot. So that would have improved it. And those are the main things. Now, when shooting it upwards, if you're shooting it to where it's near the ceiling, you're gonna have an issue with parallax. So a parallax, we're talking about, my hand is in front of what letter on the board, on the smart board. Well, what Emily would see is very different than what Marissa would see, because they're at it from different angles. So when you're looking at how far up a ball goes, if you are standing here, where you see the ball, you're gonna be looking at it at this angle right here, and so potentially you're gonna see the ball at a much higher height, a much greater height than if you're standing back here. Now, if the ball's right next to the wall, they'll probably be pretty close, but that can vary. So when you're doing that observation about how far up the ball goes, if you can sort of stand back, or if it's safe, stand on a table. Just don't fall, please. So that will help, but looking at it right up close is very difficult to do. I have some students who will put a table right next to where it's being shot upwards so that they're right there to where the ball goes. This lab gets usually pretty good results, but there was one group last year that the first part of the lab, they're trying to figure out what setting they should put it on. And they had it on the long setting and it didn't hit the ceiling, and that they insisted. They were on the long setting, it didn't hit the ceiling, so that's what they went with. So when it came time to actually doing the lab, I mean, the ceiling's 3 meters away, but when it came time to actually getting to that part where they're shooting it straight up on the long setting, it was shooting up about 6 or 7 meters. So they had to go out into the stairwell to do the last part of the experiment. I'm not quite sure where it went wrong. I have suspicions, but something went wrong. So when the first part, when you're establishing the distance, please make sure you're on the setting you think you are. And I think on that note, any questions? Then let's head on down. And I don't need to record empty space.